All right, let's go ahead and get started. Good morning, all, and welcome to the latest installment of Mazzetti's Bending the Climate Curve Learning Series. I'm Christina Sanborn, Sustainability Practice Leader here at Mazzetti, where bending the climate curve is our mission. This morning, we'll be learning about decarbonizing existing hospital buildings, focusing on electrifying heating systems. In December of 2024, ASHE published a case study entitled Electrifying Heat in an Existing Hospital, Providence St. Peter Hospital Decarbonization Case Study. This presentation will provide context for the case study, an overview of the energy use and carbon emissions from hospital buildings, and the result in terms of technologies, cost, and schedule of this extensive case study. Joining us today are Kara Brooks, Geoff Glass, and Fred Betz. Geoff is the sole proprietor of Octet Works, a healthcare sustainability consulting firm. He has dedicated 39 years of his career to developing high-performance healthcare facilities, having substantially improved environmental performance at 4 major medical facilities in the Puget Sound region of Washington state. Most recently, and for the past 26 years, he has served as both Health System Energy and Sustainability Manager, as well as Regional Facilities Director for Providence. Geoff has been a professional engineer licensed in the state of Washington and has received certifications in energy management and healthcare facility management. Geoff received his Bachelor of Science in Civil Engineering from the University of Michigan and his Master of Science in Systems Management from the University of Southern California. As the Senior Associate Director of Sustainability for the American Hospital Association, Kara Brooks spearheads strategic leadership, advocacy, and program development for the association's environmental stewardship initiatives. With over 20 years of experience in environmental sustainability and energy engineering, Kara is a recognized expert in her field. She actively contributes to numerous national panels and committees, helping to develop codes and standards for the healthcare built environment. Kara holds a Bachelor's of Science in Mechanical Engineering and a Master of Science in Business Management from Colorado State. She also serves as a subject matter expert on the National Academy of Medicine's Action Collaborative on Decarbonizing the U.S. Healthcare sector and participates in various other national technical standard committees. Fred Betz is a founding principal at NeuMod Labs in Madison, Wisconsin, where he leads data-driven consulting, research, software, and training for the built environment. With a Bachelor's in Mechanical Engineering and a Master's in Engineering from MSOE and a PhD in Building Performance and Diagnostics from Carnegie Mellon, Fred brings 16 years of experience in enhancing building performance in large, complex facilities such as healthcare centers, laboratories, data centers, academic buildings, and central utility plants. He chairs the ASHRAE 191P standard for water balances and efficiency in mechanical and process systems, and is actively involved in ASHRAE 170, ventilation of healthcare facilities, and Technical Committee 2.8, building environmental impacts and sustainability. Fred also serves on the ASHE, American Society for Healthcare Engineering Sustainability Committee. Now, today we're going to explore these 4 learning objectives, which are relevant for decarbonizing existing hospital buildings. I won't read them out to you, you can see them on the screen, but this is the focus of what our conversation will cover today. Before we get started, a bit of housekeeping. Today's event qualifies for 1 AIA HSW CEU. If you didn't provide your AIA number when registering, please send it to info@mazzetti.com. Now, we will hold questions until after today's speakers have made their presentations, but you are encouraged to ask your questions whenever they occur to you at any time during the presentation via the Q&A function of the webinar. Today's session is being recorded. With that, take it away, Kara.
Thank you, Christina, and thanks for having us here today. And I know we're getting the slide deck up on the screen. And yes, so today we're here to talk about decarbonizing an existing hospital building, and specifically through the electrification of the heating system. It was a great study that we did, and really excited for all of you to learn more about what we found in that study. Next slide, please. As Christina already said, these are our 4 learning objectives that we will be covering today. So next slide. So let's start out talking about decarbonization and decarbonization as a design strategy and why we would do this in the first place. I think this is a great quote by Dr. Victor Zhao of the National Academy of Medicine. He looked at this and he said, it's important that we go down this road because of how pollution is affecting our communities and affecting the health and the health of individuals. And so it's important that we start to look at this concept of decarbonization. Next slide. So let's start out talking about what is decarbonization and how do we define decarbonization. For a long time, and it might even still be that way, when you type in decarbonization, it comes up as a spelling error. But conveniently, ASHRAE has defined what decarbonization is as a decarbonized building is one with net zero emissions of operational greenhouse gases and 40% lower embodied emissions. And I think it's important to understand that, and also to understand how kind of the history behind ASHRAE's efforts on decarbonization. A few years ago, they developed a task force because they knew that we were going to have to start to design with decarbonization in mind. And that task force started to look at different ways. They created a position on decarbonization and why they would want to go down this effort. And then they also developed goals around the 2030 and 2050 that you see here. Along with the task force, as that was created, they started to think about what they should develop in terms of guidance to help the field learn and to understand how to decarbonize. And so they did recognize that hospital buildings are unique. There's so many unique characteristics, including, that they're highly regulated, that they are 24/7 use, and they are very energy intensive buildings. And so they said, okay, let's take hospitals out and think about this as a unique building type. And so ASHRAE and ASHE got together and developed the Decarbonizing Hospital Building Guidebook. I actually saw, when I was looking at the attendees, some of our authors are on this call with us and could speak a lot better about the contents of it, but it was a great effort, and great to see everybody here. I will say that the focus of this particular guidebook was on new buildings in North America. And I wanted to point that out because it's we wanted to address how you would design a new hospital building within this country. And it was a great effort, and this book has been available since about last June. Next slide, please. So within ASHRAE's position on building decarbonization, they saw some different process steps, including, you all can read these, but things like energy conservation, decarbonizing the electrical grid, providing on-site renewable energy. And all of these are really important strategies and steps. They can be taken with pretty much any type of building and that you want to design. But, again, we know hospitals are different. So before we get into the next slide, I kind of wanted to frame up how we ended up going down the road of looking at an existing building. So we had already looked at the new building and said, how are we going to decarbonize the new building? But the question came in as to how would is this possible within an existing building and an existing hospital building? And we really wanted to answer that question because we knew that it would not be easy, and that there was a lot of speculation that it frankly couldn't even be done. So Jeff, next slide. So how does this translate for us? As we went down this study, and Jeff and Fred are going to get in much more depth on what we did within the study, But we knew that we were going to have to look at the peak heating demand. And the interesting thing about this is as many of you are designers, when you look at the electrical load, most often the cooling load is the highest because we've been traditionally using natural gas for fuel for our heating. Well, now we need to look at that peak heating demand in terms of an electrical load. And Fred and Jeff are going to get into that a lot more. But it is an interesting way to look at things, because one of the things that we didn't want to do is to affect the grid. And that was a question that constantly comes up is, well, if we're going to electrify and you switch out a boiler for electric boiler for a natural gas for electric, what is that going to do to the grid? So we set out to not affect that grid. We also, as we start to look at this, we thought, using heat pumps and heat recovery were going to be essential within a building. We didn't really want to the extent feasible, we didn't want to burn any kind of fuel that any kind of like natural gas or fossil fuel, that instead we wanted to electrify everything. We wanted to use zero carbon and depend on use zero carbon electricity sources, and also to use beneficial electrification and to use RECs. And what's interesting about this study is we chose a specific hospital in Olympia, Washington. Jeff will be talking about this, but it was important that we did that, and we used a Providence hospital because Providence was kind of further ahead in their journey. And it was interesting because they were already using they had not renewable electricity. So all of that kind of fed into this study that we're going to talk about today, and this concept of decarbonization. And I'll let Jeff take it from here.
Thanks, Kara. Yeah, so what I'm going to do is share a little bit of our experience with the Seattle Building Performance Standards. So Seattle is one of a handful of jurisdictions that has adopted, and this was in December of 2023, emission performance standards for commercial buildings over 50,000 square feet. And these are the milestones that they have picked. It's close to a linear reduction to zero at 2045. And these largely, this ordinance or legislation has been created in the absence of understanding if it's even possible, how much it costs, how long it takes. And certainly we know that hospitals are a big challenge, and really any plant that's a central steam plant is sort of in this conundrum, if you will. So this study really helped to inform and is currently helping to develop the implementation rules around this ordinance. You can see the penalties for non-conformance are really steep: $10 a square foot. For Providence and Swedish, it's probably around $25 million if we fail to meet these targets. And one of our advocacy efforts resulted in the city allowing campuses, steam-based type campuses, to develop their own decarbonization plan for their approval. So this was a real driver in terms of doing this study, obviously. Here is a pie chart that shows actual current third-party verified emissions from Providence across our 54 hospitals. This is for 2023, and you can see the largest single contributor is what we're trying to do away with, this thermal energy piece. Understanding that in Washington, electricity will go to essentially net zero by 2030. And Providence is participating in that through REC purchase and utility purchase of renewable energy. The third biggest contributor is employee commuting, which we expect to be improved through EV and the like. These others are fairly nominal. So it's really this piece around thermal energy that is the solution to decarbonizing hospitals in Providence anyways. This is a chart that I think is really, really important for understanding how to decarbonize and what the opportunities and challenges are. So this is actually, I think, the definitive use study for hospitals. It was conducted in maybe about 15 years ago, 17 years ago in Washington State, just a little bit further south than Olympia, on a brand new hospital where a grant was given to submeter all of the principal hospital uses. And you can see here about 55% of the energy use in a hospital is fossil fuel based, 45 is electric based. So this still becomes the definitive breakdown of energy uses in a hospital. This study then modeled the energy uses at St. Peter Hospital, and though it doesn't look exactly the same, you can see that pie chart with the 45% being space heat, that that this chunk of the pie chart is pretty darn close to that 55%. So it really sort of substantiates both studies, substantiates the model for St. Pete's, substantiates the original submetered data that came out of another hospital in Washington State. So I've put little icons by those uses that really we talked about this ASHRAE first step being, what I call deep energy retrofits, much deeper than we've ever talked about or thought about before, thinking in terms of driving energy use down that low so we don't burden the grid with additional electricity than we're currently consuming, and that we don't drive up huge expense in oversizing a heat pump plant. That really kind of changes the economics of the equation. So these icon areas are really kind of the four areas that we attacked in our study to figure out how we go about making energy reduction. Space heat, obviously, being the largest single contributor. Here's a wonderful graphic, I think, from the ASHRAE decarbonization guide. It really speaks to sort of the change that we need to go through. This, as Kara said, relates a little bit more to new buildings than existing, but I think that the flow is really good. So fossil fuel energy in to a boiler, electricity in to end uses, solar in through the building exterior, conduction and radiation out, exhaust air out, cooling tower, heat rejected with a little bit of fresh air in. That is, probably 95% of our hospitals in the country right now. Here's where we know we need to go. We need to close that loop. We need to essentially we need to completely remove that fossil fuel source. We need to substitute a heat pump where we can collect heat from the exterior environment. Potentially, we might be able to recover some wastewater heat recovery. Use those electrical sources that are coming in, collect them better, minimize conduction and radiation, and completely minimize. And this is where we really take some pretty aggressive steps in the exhaust air heat recovery to limit the size of that heat pump plant, as we've said a couple of times now. So I'm going to turn it over to Fred to get into the details of our study. Fred, take it away.
All right, thanks, Jeff. Thanks, Kara, for setting the stage. So let's dig into the case study itself. It is a joint effort. So ASHI and the Washington State Society for Healthcare Engineering and Providence provided funding. So thank you for that. And so we have this existing 730,000 square foot hospital in Olympia, 370 beds, 2,700 plus caregivers. So the hospital itself was picked because it's what I would call almost generic or typical. There's a lot of facilities like this. The first phase was completed in 1969. It's been expanded 9 times since. So as we describe the facility and the challenges we face, should be a lot of overlap. So it was deliberately picked to be as comparable to others as possible. We looked at 4 different pathways to carbon neutrality. We're going to go in depth on one today. You can look at the others in the study. The focus, as Kara mentioned and Jeff mentioned, is to eliminate the natural gas use, both the carbon emissions associated with combustion, but also the greenhouse gas emissions associated with methane leaks. So we really want to disconnect, which is a big challenge, especially in the light of processed steam loads, and we're going to address those. Hot water supply temperature, we're going to make a big deal out of that because that has a huge impact on electrification. We'll show you how. We went back and forth, and I know we're going to do a deep dive here, but in the study, there's a couple of different approaches for the new mechanical equipment. We're going to touch on some of it in greater detail. Resilience is another big piece of this, as we're moving away from natural gas. Not to say that it's perfect, but it is deemed generally, not always, but generally the more reliable than electricity. And so, moving to an all-electric facility is perceived as a pretty significant risk. To finish out this slide here, the full technical report, a couple hundred pages of it, plus a how-to companion guide were published in December of last year. So it's been out for about 5 months now. So next slide, please. So as all studies should, we start with a climate analysis. Each facility is in a different location, therefore, by default, somewhat unique. And so the climate has an outsized impact on decarbonization. One, you see this gray band here, and it'll become more apparent what that is. That's the optimal operating zone for air source heat pumps. And then you see these 4 spikes, and this is actual meter data from the site through the BAS that shows what, in my experience, is somewhat unique, but it's unique to this part of the United States. Is it does get cold, albeit not often, right? So the dark black line there is the 20 degrees Fahrenheit. That's what ASHRAE says is the 99.6 design conditions for heating. In reality, it gets colder than that. It gets down to about 9 degrees. And we've measured a few times there. And so, we have to cover those conditions. So next slide, please. So one way in where that climate really impacts is on the electrification of heating. And so this is a generic air source heat pump capacity and efficiency chart versus ambient temperature. So x-axis is the ambient temperature, and you can see while that gray box there in the upper right is what is maybe often touted as the efficiency of heat pumps, so a COP of 3, and then there's their capacities and so on. The reality is that is a variable number, right? And so one of the challenges that is often surprising, and it has created this myth that heat pumps can't provide a sufficient capacity of heating, when in fact they can. You can see that, still has heating capacity down to -20. Our 410A evaporates at -55 degrees. So you can definitely heat. The catch is the capacity and the efficiency decline as you go to lower and lower temperatures. The AHRI test standard for heat pumps is for 17 degrees Fahrenheit, which, if you happen to be in a location where the heating design conditions, the 99.6, are 17 degrees, well, great, good for you. For everyone else, you need, for whichever product you're looking at or products, you need this full curve down to whatever your design condition is. So if that's 0 or -10 or -20, the manufacturer of that piece of equipment needs to give you this performance curve, because it has an impact on how much load and what quantity of units you need, and also what the electrical impact is. So, if we assumed a COP of 2 or 3 based on these cut sheets, we would be undersizing both our heating capacity and our electrical capacity. So we actually need to go down to 9 and use a COP of about 1.6, 1.8, somewhere in there. Next slide, please. So the other challenge here is the cost of electricity versus the cost of gas. And Jeff was nice enough to put these together for their system, so we knew what we were getting into. But it's about a 30% premium per kBTU of heat provided using electricity versus natural gas, just as a straight conversion. And so there's a bit of an uphill climb here. So we need to do this as efficiently as possible. You do get as you saw on the previous slide, the COP benefits this somewhat. So you need to have fewer BTUs, but we do need to account for this in order to make this whole thing cost effective. Next slide, please. All right, so I'm going to spend some time on this slide to walk you through. So as Kara introduced the topic of beneficial electrification, that is the purple line on this chart, the horizontal line there. And that's the summer peak electrical demand that's verified with Puget Sound Energy. They were a good partner in this, in addition to giving us the peak, which we also got from utility bills. But we not only needed the peak for summer, so we knew what demand we were putting on the electric grid, we also needed the wintertime peak. So it's a very common question is what is the peak electrical demand? The uncommon question is what is the peak electrical demand on the coldest day of the year? And so you see that on the lower left blue bar, that the actual peak is about 2,200 kW in the wintertime, or 2,300 kW. And so if we know that our summer peak is 3,600 and our winter peak is 2,300, we know we have, just by showing up, 1.3 megawatts of spare capacity for heating right from the start. The next challenge that is often pointed out is the capacity of heating. So you can see that big red bar on the left is the nameplate heating capacity. And this is what people will look at and say, look, our heating plant has this capacity. There's no way we can electrify this. And this is where we really, really start getting into data. And a lot of this is data driven. And it's actually the single advantage that existing facilities have over new construction. Because new construction, and I've designed lots of new hospitals in my career, ultimately it's an engineered guess, right? But we all know that the actual performance does not always align with the projected performance. And so what we did is looked at the sub-meter data for the entirety of the steam plant and found that it's actually 5 million BTUs less than the capacity. So using the nameplate is about 1.5 megawatts of too much demand. So taking the real data, we're down now to about an 8 megawatt demand in our 3.6 megawatt capacity. So the next thing we look at is what are the big drivers for peak demand in hospitals? First is conditioning outside air. And so there are dozens of air handling units at the hospital, including 9, which make up roughly 50% of all airflow, are 100% outside air. 8 of those 100% outside air units have standard runaround loops with about a 50% effectiveness, and one of those air handling units has no airside heat recovery. And so what we looked at is retrofitting those with a higher performing enhanced runaround loop that gets an effectiveness around 80%, and with that added heat recovery and replaced heat recovery, we're taking away yet another megawatt of heat demand at peak. And again, this is at peak, not average over the time, right? Another thing I'm finding with a lot of facilities that I work on, there's a lot of old envelopes. So ordinarily, this is another one of those myths, when you say, oh, we need to improve the envelope. From an energy performance perspective, especially when you're doing a newer facility, making envelope improvements is very minor incremental. The envelope has been regulated for a long time. But if you go to much older facilities, so for example, about half of this hospital is pre-energy code, you'll find a lot of windows with a U value of 1 and uninsulated walls with an R value of 2 or 3. We field measured all that. And just making envelope upgrades there, even to standard, by today's standards, let alone better practices, you're looking at 50 to 75% reduction in skin heat loss. So again, going from a U value of a glass of 1 to a U value of 0.3, which is a nice glass, not best in class, but it's a nice window. It's a 70% reduction in heat loss. Similarly, going from an R3 wall, which is mass concrete, up to even just an R12, it's a 75% reduction. And R12 is not exactly pushing the boundaries here. And so that, again, on the peak conditions, it's taking away yet another megawatt and change of our heating load. So we're working our way down towards that beneficial electrification, but those were the big demand side items. As I promised, we'd get into process energy. So as of today, and one of the key points I forgot to mention is the requirement for this project is to show that all this technology exists today. And we'll get into timeline and what that means for that technology, but this has to be feasible today. The products are, on the shelf, as it were. So the next two buckets or bars here are a variety of miscellaneous electrical savings. The hospital has implemented some, has done partial LED conversion, partial conversion to DDC controls, you name it. It's a partial conversion from PSC motors down to EC motors and so on. So we finish that implementation, save about 300 kW across the facility, but we use up that 300 kW by electrifying their process steam loads, which the two big ones in this case are central sterile and the steam dishwasher in the kitchen. There's other steam loads as well, but those are the two big line items. And again, I'm going to harp on data here. If you have 5 sterilizers that need 200 pounds per hour of steam, the peak load is not 1,000. It's not even close. It's closer to 200 than it is 1,000. And the reason is they don't all run at the same time. It's not a flat out steam demand that cycles through. And so getting sub-meter data for your sterile processing of how much steam you actually need is a huge demand savings. I can't emphasize the data enough. Okay, so now we've done all those demand side measures. We've reduced the load through a variety of ways, and now we're finally getting to our heat pumps here, so we can right size those heat pumps. Which again, with that COP of about 1.6, 1.7, we are able to get us down to just under 4 megawatts of capacity. But we're falling short. So we got to keep going. There is, again, metered 60 tons of heat recovery chiller. Heat recovery chillers are another technology that a lot of folks don't like because they don't work properly. And the number one reason they don't work properly is because they've been sized wrong. They need to be sized small, not large, which is, antithetical to how most mechanical equipment is designed. It is sized to be large, and you can always turn down from there. Heat recovery chillers need to have a place to go with both the cooling and the heating. And so since we know what the loads are, we know that a 60-ton heat recovery chiller is exactly what we need, and that will run flat out and won't have cycling issues and so on. So again, we're reducing our heating load a little bit off that 60-ton unit. And then finally, not last, but definitely not least, and it's actually one of my favorite topics here, is thermal storage. So traditionally, thermal storage is looked at from a cooling perspective to provide peak demand management for cooling systems. In this case, we're actually storing hot water, and we're actually storing it in the location of the 2 large steam boilers in the existing central plant. So as these demand side measures and new plant come online, we're able to decant that load and eventually remove those. There's a whole phasing study that we're not going to go into in detail here, but enabling that transition, because the challenge here has to be running the whole time as you're making these updates. Next slide, please. So the timeline, this is another major challenge. So according to our cost estimators and construction phasing consultants, McKinstry, that helped with this portion of it. You could do this whole upgrade in 6 months to a year if you shut the hospital down and told people don't get sick, don't have babies, don't have accidents. You can do this whole thing in a year. The reality is we can't shut down a hospital. There's no spare hospital laying around, right? And so this has to be done incrementally over many years. And so a lot of the project timelines, this is what Jeff was getting to, is why there's flexible schedules for campuses and facilities with large central utility plants. Is these upgrades need to be phased in as time allows and budget allows. And so it's a pretty lengthy planning process, but the goal, of course, is to get to zero at the end. Next slide, please. So the results, we show that this is technically feasible. And here's a laundry list of things, some of which I talked about, of what would need to get done. Upgrading the heat recovery on 9 of the air handling units. A few of them, and this is something I kind of neglected to mention, a few of them are listed in the facility condition assessment as needing to be replaced anyway. So rather than replacing systems in kind, I would look at any system that you're working with at the moment. If it needs to be replaced, look how you can enhance that piece of equipment that can then work towards your goal. We do need that dedicated electric boiler for sterile processing. There are the first few products now on the market of steam generating heat pumps. They're not ready, what I would call, for this task yet, because most of them make 2 and 3 psi steam. For sterile processing, you really want to have something around 40 to 80 psi steam. But to me, that means that in this timeline, which you just looked at, 10 to 15 years is a long time in the realm of product development. 10 years ago, we couldn't have even done most of this work because the technology didn't exist. So another 10 years from now, it's plausible that there's something better than an electric steam boiler. Similar with the kitchen equipment electrification. It's actually a heat pump conveyor dishwasher that's being used here. Replacing the windows, we talked about envelope. The phasing of the steam distribution system, we did include that at length inside the case study. This is really a case-by-case basis, so hopefully it gives you some ideas, but each steam distribution system is unique and brings its own challenges. As part of this plan, there is we're adding about 1 megawatt of generators to support the heat pumps for the wintertime load, because right now the boilers are on fuel oil for the winter for emergency operation in the winter, so we need to have something similar. One little nuance there is we're using the generators as a cogen system, but only for emergency use. So if those generators are operating in the winter and there's heat demand, so for every megawatt of power a generator, fuel oil generator makes, about 1 megawatt of jacket heat and 1 megawatt of exhaust heat, give or take, is generated. And so we're able to use that jacket heat during a power outage and essentially have a heat recovery system built into our emergency operations. So we get additional heating beyond what we have with the storage and any heat pumps. And I think I touched on heat pumps and thermal storage plenty. So next slide, please.
Hey, Fred, could you talk about the heat pump plant as an addition to the central utility plant, as opposed to trying to work within the existing footprint of the central utility plant?
Yeah, absolutely. So there's an existing plant. Actually the first thought was to put a penthouse on the roof of the plant, keep it within the same footprint, relocate equipment that was on top of the existing plant elsewhere, and some of it would be no longer needed because some of it was associated with the boilers, and tie in the electrical system, the existing electrical system. That's part of that beneficial electrification. We could use the same electrical service. Our cost estimators and construction consultants helped guide us towards an alternate solution. So to build a in addition to the central utility plant to the south, rather than building on top of it. One is being less disruptive, but two, it actually ends up being cheaper. So that was a bit surprising to me that doing it that way was cheaper, but the numbers bore that out. We also opted to add an electrical service, but let me be clear here, we're not adding load to the grid, right? So within this cost, there is an additional electrical service. So essentially we're decanting a whole bunch of load off of the existing electrical service and moving it to the new electrical service. So the net is not increased on to Puget Sound Energy's load. But it was actually simpler to just put a new service in and build this plant separately rather than try to splice it in with the existing plant. So something to be considered, again, on a case-by-case basis. Thanks, Jeff. Okay, so results. We did start with meter data. The EUI is 202. That is already pretty good. The hospital's been pursuing energy efficiency for many years. One thing I didn't actually mention, which I would do in nearly every other hospital, but was not necessary here, is the airside systems. They're already down to code minimums for air change rates. The patient tower is a dedicated outside air system, providing 2 air changes of 100% outside air, plus zone level or patient room level fan coil units. And I mentioned that those were getting motor upgrades, which had a pretty significant reduction in peak power. So we took all that data there and we made it a calibrated energy model, which is per ASHRAE guideline 14, if memory serves. And applying all these measures would drive the EUI down to about 125. So pretty significant reduction. The number that people most are interested in is, what does this cost? So there are 4 different scenarios posted. The one that we presented here was about $93 a square foot, which is about the same cost as a tenant improvement. Couple catches though on that. One, it's not just a tenant improvement to a piece of the hospital, it's the entirety of the hospital. So the square footage is the full square footage. The other part of it is there's a limited parts at the tenant improvement or of this upgrade that the patients and staff will experience directly. I do want to especially highlight those envelope items. Again, thermal comfort there that is driven by those peak loads on hot and cold days. They do have issues there in some of the facades, the older facades, and so upgrading that would provide benefits. But by and large, this is a behind-the-scenes tenant improvement. The timeline, the full 15+ year timeline is needed, and will be needed in most existing hospitals in order to implement this. So one of the things that we included in this is we are not including any incentives or whether it's utility, government, et cetera, because of the timeline of this. Most incentive programs are much shorter. And so that is the full, $93 price. Another point of reference, some folks have asked, and there's a section on this in the study, why not just build a new hospital? A new hospital will go for somewhere between $900 and $1,000 a square foot. So from a cost perspective, it is substantially more, in addition to the embodied carbon losses from the materials, which is also included in the study. So it's much more cost effective to take an existing facility and do this work than it is to build a new one, albeit I would grant that the renovations are more disruptive to existing operations. So, and finally, the hospital already purchases 100% renewable energy. So that's all baked into the cost from Puget Sound Energy. They were involved in this project. So, but when, the bottom line here, when complete, on-site building emissions will be limited to generator fuel and those occasional outages that happen and refrigerant leakage. And if the world of microgrids with batteries and such continue to progress, maybe in 10 years or so, the generators won't be needed either. And similarly with refrigerants, we didn't spend a whole lot of time, but that's perfectly plausible that in 10 years, the refrigerants will basically be zero GWP or close to it. So I think that is my last slide. And back over to Christina.
Great, thank you so much. I know I learned a lot listening to your presentation today, and we have some great questions from the audience that we'd like to address. So I'm going to share my Q&A screen. And thank you. I'm just going to share this. So we've had some good questions. In fact, one of them is focused right on that utility piece that you were just talking about, Fred.
Mm-hmm.
So one of our attendees asks, in regards to the concept of not interrupting the grid or disrupting the grid, did you query the utility companies about this? My understanding is that some utilities, such as PG&E, would like to partner with health systems to help hospitals electrify.
Mm-hmm.
You mentioned that you worked with the utility company in the process of doing this. Maybe you could expand a little bit on how they were involved.
So I think for the study, where they were most involved is providing data. Getting into the weeds here a little bit, but submeters in hospitals, they're not necessarily utility grade meters. So Puget Sound Energy did have at 15-minute increment data at their at the utility meter for this facility, and so we were able to move forward with a lot of confidence there. So they are aware of this study. One of the things I didn't talk about, and it's in a different, it's in one of the other pathways, which was just to say, well, the heck with it, we're going to replace 2 big boilers with 2 big electric boilers, and then we'll be electrified, and we'll buy 100% renewable electricity, and we're done, right? Which is conceptually simple. The operational cost impact is pretty atrocious, and the impact on the utility grid is pretty severe. And so, I mentioned that looking at different cost models, we didn't include the cost to the utility. So we went towards let's make this beneficial electrification concept achievable. If you increase demand for electricity at peak, and you want it to be 100% renewable, the electric utility is going to have to spend money in order to provide that. And so to their questions, I think utilities should absolutely be working with hospitals, especially in any areas that have limited capacity, because depending on how this goes, it could be a lot cheaper to use less at the hospital than to just shift the problem onto the grid. And so the electric utility might actually save money by providing incentives towards the beneficial electrification goal, because there's cheaper, easier ways for hospitals to do this, but they then create an enormous problem for the grid and for their own utility bill cost.
And I would say, Christina, it was a little bit out of the scope to get in an in-depth discussion with the utility. We were really trying to answer some basic questions. Is it feasible? What's it cost? How long does it take? And in this case, the electric utility is also the gas utility. And our state is definitely positioning itself to move away from gas on this kind of a timeline. So it's understood by policy that Washington State intends to move in this direction, and this is sort of how a big anchor hospital can help support that journey.
Thank you, Jeff. Our next question is about the energy breakdowns that you showed, Jeff. So maybe you could answer this one. Were the systems that were evaluated constant air volume?
Well, I think Fred did touch on that a little bit. I think about 50% of the ventilation systems at St. Peter Hospital are outside air, and I would say probably 85 to 90% are constant volume systems. So that is he did mention that we're doing everything we can to lower air volume. There probably is some opportunity, some fairly limited opportunity, but still some opportunity to move in some areas, possibly from constant volume to variable air volume. But well, most of the air movement in the hospital is constant volume.
Yeah. And let me add to that there's by reducing the peak loads, we reduce those airflow rates needed, right? So there's the code minimum air change rates, set by standard 170 or others, depending on where you are, that you have to maintain regardless. And so in a lot of parts of the hospitals, it's already at minimum. So ordinarily, I would actually start there because it's usually a lot of opportunity there. But in the case of St. Peter, it was already mostly at code minimum with a handful of exceptions. Not so much as to, at least initially, we're looking for big, megawatt level saving items, which in another hospital that I'm working on right now, that is definitely the case. There's probably the single biggest value there is to convert from constant air volume to VAV, because they are not near code minimums. They're maybe twice that in some cases.
Wow. So a listener offers congratulations to all of you on this historic case study, and one small step for Providence, one giant leap for healthcare. Did you consider geothermal heat pumps too? And if so, what were the reasons to choosing the air source heat pumps?
Absolutely. So the outpatient, let me answer the first question first. So geothermal, yes. There's only enough space on campus to support the outpatient wing, and it also has some green space near it with the two stormwater retention ponds there. So there is a section in the study there that allows for that. The cost wasn't great, and it wasn't absolutely necessary, although it does come with an advantage. And again, in this specific instance, because that outpatient section of the hospital is a little bit away from everything else, and getting low temperature hot water over there is a challenge. So we did look at and have suggested a second plant that supports that outpatient wing, should it be ever built, and that would be a ground source heat pump system. The site, while large, is pretty tree covered, so we'd be cutting down trees to make that work, which is not really a good greenhouse gas move or carbon move. And similarly, parking is pretty darn limited already, which I experienced firsthand myself of finding parking spaces there. So digging up parking lots and putting heat pumps or geofields underneath those, while technically feasible, would be even more disruptive. And so really, it was the practicality of using air source heat pumps. We did find, and this is something that's in the study, and there's more in the way, we did find large heat pumps. So the bulk of air source heat pump market is for residential and light commercial. There are some manufacturers that make 300-ton or thereabouts heat pumps, because if you use those little ones, you end up with 85 heat pumps, and the facilities manager and the maintenance techs will hate you for life. So don't do that. But we were able to, with the unit that we designed around, it's 5 heat pumps for the, if I recall correctly, for this scenario number 3. Again, different scenarios have different loads and different numbers of heat pumps, but yes, there are large air source heat pumps available.
I would just add, Christina, and thank you for the comment about the ground source geothermal. Definitely a great technology if you have the land and site to adapt it. And we're trying to do that at about maybe, what is that, a fifth of our campus or so, sixth of our campus. Point I wanted to make in all of this is from a facility management perspective and an infrastructure planning perspective, you really have to make decarbonization your North Star and evaluate almost every decision you make against that North Star, or else you run the risk of going backwards and having to rip something out when we know this is where we have to be in, by 2040, 2050. So I think it's a really critical point, and I've learned it in the process of this study, to have a decarbonization plan and then overlay that on your infrastructure plan. So as you're replacing fan systems, you're including heat recovery where appropriate. And when you're replacing your dish machine, it's a heat pump dish machine, et cetera, et cetera. I think it's every little thing is going to add up here and ultimately may have to be redone if not factored into that kind of an approach.
We're running short on time, so I have to pick one of these great questions as a last question. I think the penalty question is interesting. So you mentioned that there are penalties for not achieving Seattle's RPS goals or decarbonization goals. What is that penalty? What's the frequency of that penalty? Is that a one-time penalty or is it annual? How is that structured? As long as you stay out of compliance, are you paying that fee each year, or how does it work?
Yeah, great question, and one that we're still kind of wrestling with Seattle to actually, in rules, clarify. But I think the intention is sort of the end game, getting to net zero by 2045. That's where the penalty comes. If you're not there on that at that net zero date, that's when that $10 a square foot penalty kicks in. But it's not intended to be like an annual penalty or even a 5-year, cycle type penalty, as it's been explained to me. We would see this once, but it's 1/10 the cost of implementation, so it's not insignificant.
Yeah. Great. Well, we do have a couple of leftover questions that we didn't have time to get to, so I'll be asking you, our panelists, to answer those questions, and we'll send out the responses to these questions when we send out the recording and slides from today's presentation, so that everybody can hear your answers virtually anyway. Great. Well, thank you so much for today. This has been incredibly informative, and I found it really enriching to listen to. So thank you each for your participation, and thank you attendees for such great questions to keep the conversation going. Now, please mark your calendars for the next Bending the Climate Curve learning event on June 17th at 8 a.m. Pacific, 11 Eastern. Our speakers will be Greg Evans, who's the Corporate Director of Sustainability at Penn Medicine, Josh Kepner, Energy Manager at Penn Medicine, and Austin Barrelin, a Senior Decarbonization Engineer from here at Mazzetti. The panel will discuss Penn Medicine's journey from making a commitment to a GHG reduction goal to a concrete plan of action and details about how to measure greenhouse gas emissions in healthcare settings. So a little bit of how to and a little bit of what we've done. So thank you so much, everybody. Have a wonderful day and enjoy the spring. We'll see you soon.